Good afternoon. We are moving on to Chapter 5 now. It's called The Human Population and the Environment. It may seem a little strange that we're talking about population, human population, in this course, but as you may or may not be aware of, human population does have an impact on our environment. It has both positive and negative impacts. Or to use terminology from the last chapter, I believe it was chapter 4, population, human population, can produce a positive feedback and or a negative feedback. And in many cases, they provide both positive and negative feedbacks. So for instance, just to remind you what we mean by positive and negative feedbacks, if we begin to look at human population, and let's just say it increases exponentially, and we'll talk about exponential growth here in just a few minutes. But if it grows exponentially, then our population will reach something called a carrying capacity limit, and again we'll define that later, and then population begins to drop off rapidly. So an increase in population can lead to factors such as diseases, the spread of communicable diseases, vector-borne diseases, which would lead to a decrease in population. So that would be an example of negative feedback in terms of human population. But we'll get to that here in just a few minutes. The overview of the chapter, sorry about that, I just lost that. Okay, so I've got the screen back on. The overview of this chapter will talk about concepts related to population dynamics. Dynamics is just a term that is used to mean change, fluidity to any type of situation. So the change of population. So we'll talk about concepts related to population dynamics. We will also look at both the analysis and estimations of future population growth. We'll talk about the age structure. The age structure of populations play a role, an influencing role, in either the increase or decrease of populations. We'll talk about something called the demographic transition, which is really fascinating. It's a set of periods that we've gone through in history that has shown how our birth and death rates have changed from time to time. I really enjoy this particular section of this chapter. We'll also look at longevity and the effects it has on population growth. We'll talk about specific effects that the human population growth has on our environment. And then toward the end of the chapter, we'll estimate, or we'll talk about the various agencies that have estimated how many people, the maximum number of people, could exist on Earth. And there are 3 different ideas on that we'll cover toward the end of this chapter. And then, here's the $64,000 question. Can we achieve zero population growth? Do we want to achieve zero population growth? So we'll look at that toward the end of the chapter, but we have to get up to speed on some of the terminology and other areas within population dynamics. So I think you're going to enjoy this. Let's see if I can get down to the next slide here. Nope, that's not it. I apologize. I'm having a little problem getting from slide to slide here. So, some of the concepts of population dynamics, or terminology, that you need to be familiar with as we step through this particular chapter. So when we talk about population dynamics, I mentioned that earlier, it's just basically studying how population changes over time. Population itself, we will define as a group of individuals of the same species. For instance, we'll really focus on the human species living in a particular area. And then species itself, all individuals that are capable of reproducing. A species is made up of populations. So we could talk about different types of species, but for this particular chapter we'll focus in on human population. Demography is basically the study of human populations. Now, if we look into the concepts related to population dynamics, there are several properties here of any population, and we'll define each of these here in just a few slides, but we'll talk about abundance, birth rates, death rates, growth rates, and age structure. And when we talk about these various terminology, we're going to talk about it in terms of per 1,000 people. Okay, so that's how these are often reported. So when they talk about birth rates, when you hear about birth rates or death rates of nations, they're talking about in every 1,000 people. So you might hear something about 60, a birth rate increase of 60 per 1,000 people. Now, the types of population growth, we actually talked about this in the last chapter. We talked about exponential growth. And recall, and in fact, your quiz that you're working on, I think, this week, one of the questions has an answer of exponential growth, and that's simply a population increasing by a constant percentage per unit time. So let's just say 2% increase per year, or a 2% increase per every 10 years. It's just a constant percentage. In other words, the percentage doesn't change per unit time. So we're talking about a fraction here. So again, I'm using the example of 2% per year. Now, what's interesting is that our population growth has already peaked. And in fact, it peaked some 40 years ago. Between 1965 and 1970, I believe the human population growth that's in your textbook, it was either 1.6 or 2.1%. I can't recall right now. But at that point, at the time this book was published back in 2012, the human population growth is now at 1.2% per year. So if we look at this, and we use the example of 2%, well, I should back up here and talk a little bit about what this graph is. It's about population growth. So you notice here on the x-axis are the years, and the population in terms of millions. So we've got 50 million, 100 million, 150, 200 million, 253, up to 350 million. So we're talking about U.S. population growths in terms of millions. So we start back at 1790. Notice you've got two curves here. The red curve is the actual population growth, and then, is the forecasted population growth. That would be using the exponential growth rate of 2% per year. Okay, this is the forecasted population growth, the red curve here. If we were to look at population increasing at 2% per year, you see the forecast. Now, the actual growth rate is exponential, but it is at a higher rate. So our growth rate actually was higher than 2%. And in fact, what do you notice? As we start out here back in 1790, just shortly after the birth of our nation, when a census was taken, we see that both the actual population growth and the forecasted population growth were running neck and neck. And you would expect that for lower levels of population. But as you see, they begin to diverge right here at about 1850. So now the actual rate of increase is larger than what you see with the exponential curve, or the model, the forecasted model. And so we had a much greater rate of increase of population in the U.S. And they actually come together, surprisingly. I believe this is right around 2008. 2010 is here. You see the years down here. That the U.S. population and the forecasted population is just a shade over 300 million. So notice here again, the actual rate was greater than 2%. So again, notice the actual and the forecasted both grew exponentially, but the growth rate for the actual was greater than 2%. So let's concentrate on the history of human population growth. There are various stages that we're going to look at, and I've got a graph here of stages, but it's broken down into stage 1, stage 2, stage 3, and 4. And actually there's a stage 5 mentioned in your textbook, but we'll look at these first 4 stages. So stage 1, you see, was back toward the beginning when we had hunters and gatherers. Total population you see there was less than a few million. Now again, this is human population growth of the world. Then we entered into stage 2, and your textbook actually talks about specific dates when we entered into stage 2. But during stage 2, we begin to see advances in agriculture, so we didn't have to necessarily depend on the hunting and gathering of thousands and thousands of years ago. We actually begin to use the Earth's resources, the Earth's land, and to produce food. And this rapid production of food and availability allowed for our population to begin to increase, specifically the density of population and the increase in human population. I believe it's in your textbook. It talks about at the beginning there were so many square miles, or one person per square mile, and at the beginning of human population, it was a rather large number. I just kind of chuckled at that, and then it gave examples of a 20 by 20 square foot, 20 square feet of land available for each person on Manhattan Island. So imagine yourself standing in a 20 by 20 square foot patch of land. That would be your piece of land. So it's kind of interesting. Then we get to stage 3, which is defined as the Industrial Revolution, and if I'm remembering my history right, that would be right around 1750, somewhere in that area. Stage 3, again, begins at this particular moment in history, and we've also seen increases or improvements in health and food supply. This also led to a rapid increase in population. Then we move to stage 4, which is where we're at currently, and now we've seen in stage 4 that the rate of growth has slowed in developed nations. But in less developed nations, we're seeing population still growing rather rapidly. And we'll talk about the reasons behind that here a little bit later. So here is this graph. This goes back 8,000 years, and human population in terms of billions. So again, this is in terms of billions. Notice from 8,000 BC to right here, which would have been, about 1850? It's kind of hard to estimate here, but at about 1850, the human population was less than 1 billion. In fact, it was rather stable. You see a gradual increase here, and then a slight decline. And we'll talk about what these increases and decreases in population are attributed to. But it's relatively stable throughout the first, it looks like about 9,000 years. And you see this dip here, which was related to the epidemic, the Black Death epidemic. And then you begin to see population increasing rapidly. And then since 1850, check out the slope there. It's just incredible how population has just zoomed up to a current 7.1 billion as of the year 2000. Obviously, that's not current, but as of about 2000, the world population is estimated at about 7.1 billion. So the biggest growth from going less than a million in 1850 to 7.1 billion, a seven-fold increase in roughly from 1850 to 2000 in the last 150 years. If you go back the last 8,000 years, we've not even come close to seeing that type of increase. So we'll talk about why that has happened. Now, in your textbook, Table 5.1, there are some terms that you need to be familiar with. I'm not going to go through all of these, but I'll go through a couple of these. One is called the crude birth rate. So basically, it's the number of births per 1,000 individuals per year. Now, again, recall when we're talking about population dynamics, when we give numbers, we're talking about typically per 1,000 individuals. And the reason it's called crude is because the population age structure is not taken into account. Now, we don't know what the age structure is at this point. That's later in this particular lecture. But for now, we call the crude birth rate because we're not looking at age structure. But again, you can think of it just as the number of births per 1,000. The death rate, you see here the number of deaths per 1,000. Growth rate, this is the difference between the crude birth rate and the crude death rate per 1,000 individuals. Now again, this can either be positive or negative. If you have a higher death rate than birth rate, then your growth rate will be negative. Fertility, basically we're talking about the childbearing ages, the pregnancy or the capacity to become pregnant or to have children. Now there's something called the general fertility rate, and this is the number of live births expected in a year per 1,000 women, and now we have an age range, 15 to 49. So it actually defines the childbearing years. We've got the total fertility rate, and this is basically the average number of children per woman throughout the childbearing years. Now we've got a graph where we'll look at total fertility rate. So again, this is just the average number of children per female during the childbearing years of 15 to 49. Now, I'm not going to go through the rest of this, but I would suggest that you review this terminology because we're going to use it as we go through this particular chapter. So it's good to be familiar with the terminology. Again, that's Table 5.1 in your textbook. So let's talk about specifically the analysis and the estimation of future population growth. Now, in the previous chapter, we talked about exponential growth and doubling time, so you should be familiar with that. But when we talk about doubling time, we're talking about the time that's required for a population to double in size. And the way we get that is we take the number 70 and we divide that by the annual growth rate. So in the example back here, we were talking about a growth rate of 2%. So if we take 70 and divide by 2, then you can expect a population to double in size every 35 years. So if we go back here, and we're talking about the forecasted rate, okay, this is the 2% increase. As you go from year to year, you expect a doubling every 35 years on that. So if let's pick out 1910 here. We've got 50 million people. So in 35 years, we should expect to go from 50 million to 100. And so if we go 1910 and 35 years into the future, which is 1945, which would be about right here, indeed, you see, we have doubled our population to 100 million. So here are some examples that the book gives. So the U.S. has a growth rate of just a shade over 0.5%. If that is maintained, then we should double our size of population in the U.S. in almost 120 years. Now compare this with Nicaragua, who has a 2.7% growth rate per year. They're going to double their population if growth is an exponential number. If we are modeling an exponential growth, they will double their population in 26 years. So relatively small increase from 0.6 to 2.7. you see the number is dramatically reduced, 26 years. Northern Europe, a lot less growth, in fact, less than what we see in the U.S., so they are looking about 350 years to double their population. So again, this is with an exponential growth model. Here's an example of doubling time. So again, you've got growth rate and percentages here, the time to double in years here. So if you have a 10% growth rate, you take 70 divided by 10, that's 7. So it takes 7 years to double the population. So you know, as you notice, as the growth rate decreases, the longer it takes for population to double. And what you have here, if you were to connect the edges of these bars, is an exponential. It would be a negative exponential, but an exponential nonetheless. So let's talk a little bit about world growth rate. We actually peaked back in the 1960s. So you look here in years from 1950 to 2010, and growth rate as a percentage. So back in 1950, which was the beginning of the, think about it, the troops coming home from World War II and starting families. And so you begin to see this increase in growth in percentage. Went from 1.5 to 2% in a span from 1950 to 1958. And then you have this dramatic, well, I shouldn't say dramatic, but you have a 0.5% drop as we head to 1960, and then again an increase in growth rate as we headed into the early 1960s. So you see the peak here. The growth rate was about 2.2, 2.3%. World population growth back in the early 60s. Since then, we have been on a decline. And there are reasons why it has been declining. We'll talk a little bit about that as we go through this particular chapter. So currently, the world population growth is 1.1%. The time for a world population to double, if we take that number 70 and divide it by 1.1, the world population doubling is 66 years. Now, there's this other type of growth. Now, we've talked about the exponential growth and how to double your population. We've got something called the logistic growth curve, which I believe gets us closer to a truer prediction, but this model still is flawed, and you'll see why here in just a moment. And what this logistic growth curve shows is that growth cannot continue forever. If we go back to the exponential growth, this forecast, it just continues to grow and grow and grow forever. And obviously, our Earth cannot maintain unchecked growth forever. We have finite resources on Earth. So if we go back here, so basically it cannot continue forever like in the exponential growth. Now notice here, the exponential growth takes on the shape of the letter J. And will continue to go up and become even more J-like as we go in time. However, the logistic growth curve is more of an S-shaped. And in fact, I actually have a slide here I want to show you. So again, here is the exponential growth model, population size with time. It just grows unchecked. However, with the logistic curve, it has this S shape. And you will notice here that it's very exponential. So it's taken from the exponential growth model, and it looks very much like the exponential growth that you see here. And then you see a rapid increase but it doesn't continue unchecked. It then begins to equal out, and it actually follows parallel to something we call carrying capacity. We talked about carrying capacity, I believe, in the last chapter as well. And just a reminder that carrying capacity is basically what our Earth can sustain. Our Earth can sustain a certain amount of population size. And so you see population size, the Earth has a carrying capacity somewhere up here, and that with logistic growth, we eventually will reach and go parallel, and with time begin to move downward away from the Earth's carrying capacity. And in fact, we know that the Earth's carrying capacity can also decrease as well. But again, the advantage of this is that it's not unchecked growth. Okay, like I said, it's S-shaped. The growth is exponential up to a point which we call the inflection point, where, and in this example here, let me go back here, this inflection point begins to change about right here. So it begins to go from unchecked growth to checked growth and levels out here. So right about here is the change from unchecked to checked growth. And we said it reaches an upper population limit, and at that point the logistic carrying capacity and the growth is now 0. Again, you see that right here. So that is the difference in terms of exponential growth and the logistic growth curve. Now, like I said, it's not a perfect model. There are some serious limitations to the logistic growth curve. We find that populations, both in the animal and human populations and different types of species, rarely follow this growth curves. It also involves unrealistic assumptions such as a constant environment, and we know that our environment doesn't remain in a stable state. We talked about that, I think, back in Chapter 1. It is dynamic. It is changing. And the carrying capacity, we talk about a constant carrying capacity. Well, the carrying capacity of the Earth will change with time. If we begin to deplete the resources of the Earth, what the Earth can support will decrease. So again, if I go back here, and I see I have a constant carrying capacity, it doesn't change. In other words, the carrying capacity of the Earth has a certain population size. We assume that it doesn't change. That's not true. It can go down if we begin to deplete the resources of the environment. And it also assumes a homogeneous population. In other words, each person has the same impact, either positive or negative, on the environment. We know that's true. That's not true. That's not true among nations. If you look at developed nations like the U.S. and China and Europe, we have a much greater impact on the environment than, let's say, the continent of Africa or the continent of Australia or Antarctica. So that is an unrealistic expectation as well. And this logistic growth curve is also unlikely or a good representation if death rate continues to decrease. So there are the limitations of the logistic growth curve, but it is better than the exponential curve. So I hope you see the differences there. So let's take a look at some of the projections of human growth from the United Nations. There are 3 possible scenarios here. It's talking about world population from 1950 to 2010. And you see the green is what we call, I should talk about this a little bit about the graph itself. So we're going years here on the x-axis, 1950 to 2150, and then the population in billions. Okay. So if we assume a total fertility rate, again, let's go back and review what total fertility rate is. So you see it here, total fertility rate. It is the average number of children expected to be born to a woman throughout her childbearing years. So we're talking about the number of children per female during childbearing years from 15 to 49. So if we assume a constant of 2.5 children per female in the world, that's this green line here. This is the exponential. You can see right there, very much like an exponential growth there. So constant, it doesn't change, 2.5. However, if we change it from 2.5 to 2.1, what we call a slow fertility reduction, so we reduce the number of children per female from 2.5 to 2.1, you notice here the blue line, population from 2010 to 2030 to 2050 to 2060 continues to increase, but the rate of increase is getting smaller and in fact begins to stabilize. This is what we call that S curve. So again, right here it begins to stabilize right around 11 billion. We're talking about world population around 11 billion. If the average number of children per female is reduced to 2.1. If we go with a rapid fertility reduction, so in other words, we say that the number of children born per female is 1.6, so we've reduced it from 2.5 to almost 1.5. You notice that population still increases from 2010 up through about 2040 and then begins to decrease. So the population actually begins to decrease if we reduce the number of children birth per female. So there are the three possible projections of the UN. And again, this is based on potential total fertility rates. So you can see right there the impact to the world population if we only look at the total fertility rate, the number of children born per female. So one less child per female can make a difference by 2050 from, looks like about 4 billion all the way to 26 billion. That is a huge gap. It's even a rather large gap from 11 billion to 26 billion, going from 2.5 to 2.1. So let's talk about age structure. Age structure definitely plays a role in population dynamics. And the age structure is based upon exponential and logistic growth curves. They actually ignore characteristics of the environment. So looking back here at these exponential and logistic, they actually ignore characteristics of the environment that affect different age groups. In other words, we're missing part of the puzzle, such as food availability, water availability, shelter, diseases. These growth rates do not take into account what these things can provide to populations. So again, these are incomplete projections because we're not taking into account these particular parameters. Age structure actually shows us how things are divided among age groups. And this can give us an idea about not only current social and economic conditions, but what will happen in the future. And this will be more clear once I actually show you the graphs here. And the age structure can show the impact on the environment. So this is an incomplete part of the puzzle. But if we look at age structure, if we look at this along with age structure, it gets us closer to a true estimation of world population. Now there are 4 shapes of age structure. Before I get to that, let's take a look at this particular graph here. Now notice on this graph, it has percent of population on the x-axis, and it has age on the y-axis. And so we're looking at the country of Kenya on the continent of on the continent of Africa. So we're looking at the percent of population at different ages. So you notice from newborn to 4 years of age that we typically have 16% of that population made up of males under the age of 4. And if we look at females, they make up roughly 15%. Those females that are under the age of 4 make up roughly 15% of the population. So between these two, you see that 31% of the population is made up of newborn to 4-year-olds. And in fact, that is the highest population structure in Kenya, is made up of children under 4. Now, if we go up here to the 80-plus range, we see that roughly we have a percentage of about 2.5%, or about 2% of the population made up of females over the age of 80. So right away you can tell immediately that the largest population structure is made up of rather young people in Kenya. In other words, we don't see a lot of people living to even middle age, and certainly not old age. So the population, the age structure of the country of Kenya in the continent of Africa is made up of basically individuals under 30 years of age. So you start asking yourself, why does that happen? Well, we'll talk about that here in a few minutes. So this is what we would call a pyramid page. It looks like a pyramid. See how I'm kind of outlining it here? And with a pyramid type of age structure, your population is concentrated in the younger range. There is a high death rate. There's a short average lifespan. I mean, you can tell right here that the average lifespan for a child in Kenya is very low compared to, for instance, Germany. Here's the structure here in Germany, and I'll come back to that in just a moment. So that would be the representation of a pyramid. So if I say to you that this particular type of population has a pyramid type of age structure, you would say, okay, most of the population is concentrated in the younger generation, and they have a shorter lifespan and a higher death rate. Now, we can invert this pyramid. We turn it upside down. So now you would have the higher percentage of population being older, and younger people making up less of the population. That would tell us that basically we have a large elderly population and small youth population, so then we would have declining growth. So if we have an older population, so basically the idea is here is that there's not as much procreation going on. We don't have as much younger population, so we would see declining growth. Another type of age structure is what we would call a column, and that means that the birth rates, both the birth and death rates, are low, so there's basically little change in population size. So it's literally like a column. Now, what you see here, this is from Germany, the age structure of Germany. We see kind of a column. However, there's this bulge right here at about 40 to 45. And so this column with a bulge means that events in the past caused a high birth rate. Okay, you see right here we have high birth rates. I guess I should back up. I'm kind of jumping ahead here. So we've got several different things going on here. In this particular graph, everything in green is from 2010. So we see that if we look on the male side of things, we see that newborns make up about 2.5 million, or actually just a shade over 2 million in 2010. The projection for this age group of newborns for 2030 is this purple, and the projection out there is 2.5 billion. So in other words, we're seeing an increase in births from 2010 to 2030. So that means the population will be growing. In fact, we see more births than older generations, so we should begin to see the population increasing. And the same thing goes for 2050, the year 2050. You see this teal color here. They're projecting newborns. Again, I'm looking at 0 here. Newborns making up males just short of 3 million, and the same thing for females, just short of 3 million. So this tells us, or this shows us, if these projections are correct, is that we're going to have an increase in population. So there's a lot of information you can get off of this particular graph. So for instance, now this graph was made in 2010. So you see right here, those that lived to be 80 in 2010, just a shade over 1 million in terms of females. Now, 20 years later, in 2030, okay, those that reach 80 will be 1.5 million in terms of females. So you're not only increasing the birth rate as we go through time, we're also increasing the number of people that are alive by the time they reach 80. And so this is definitely a structure where you will see growth in here. So there's a lot you can tell about the age structure because it talks about birth rate, death rates, and infers birth rates, death rates, those types of things. Okay, let's talk about demographic transition. This is the area that I really am fascinated by. There are different stages. We'll talk about each of these stages 1 through 5. But before we do that, I've got a couple of graphs here from the textbook, and we're looking at years here on the x-axis and the rate of births and deaths, death represented here by the green, births represented by the red. So we're talking about the rate per 1,000 people. So if we go back to 1775, and this is for developed countries, not developing countries, but at the time what would be considered developed countries. We go back to 1775, we see that typically there were 40 births per 1,000 people. Okay, so that would be 4% growth there. I'm sorry, 4%, not growth, but 4%. And then you would have, it looks like about 35 deaths per 1,000 people. You take the difference there, you're talking about a net gain per year back in 1775 of 5 people per 1,000 population. And so for developed countries, as we went through time, you see the gap here between births and deaths. The gap begins to increase. And so as the difference between birth and death, we begin to see an increasing population. Now, after a while, you begin to see the birth rates decreasing, and there's a reason for that, and we'll get to that in just a few minutes. And then the amounts of death, or the death rate, I should say, begin decreasing as well. And for a while here, from about, the late 1800s to the early 1900s, the birth and death rates, the rates of change are about the same. So probably growth leveling off. And then you reach here, looks like in the early 1900s, the birth rate drops and the death rate increases. So the difference between the birth rate here and the death rate here, notice that gap is now closing, which means the population growth would begin to decrease. But again, you see as we go through the 1900s, birth and death rates decrease in developed countries. Now, if we go to developing countries over here on the right, we see that birth and death rates actually remain pretty similar. Okay, so the number of births per 1,000 people from 1775 to 1825, and the deaths per 1,000 people, the difference was about the same. So about 40 per 1,000 people were born in 1825, and about 35. Going over here, picking off the numbers, about 35 deaths per 1,000 people, which added a net of 5 people, or 5 per 1,000 people. Now, as we go through time from 1825 on up to, looks like close to 1875, the gap between birth rate and death rate in developing countries begins to get smaller. Okay, so the birth rate hasn't changed appreciably, but the death rate has increased. And so now the net gain between birth and deaths is now down to about 1 per 1,000 people. So population growth not occurring, or the growth rate is decreasing. And then after 1875, again, all the way from 1775 through almost 1955, almost 200 years, the birth rate in developing countries is rather stable. But you look at the death rate, and then all of a sudden we hit about just short of 1925, all of a sudden the death rate in developing countries begins to decrease dramatically. Birth rate remains the same, a little bit, actually an increase here, and then eventually it begins to drop off. But any idea why the death rate dropped off dramatically in the early 1900s? Now this is in developing countries. Well, part of it may have to do with, recall, we talked about resources that could impact. We talk about food, water, shelter, diseases. So in developing countries beginning in about 1925, going through to 1990, we've had increases in food production. We've had cleaner water. Some diseases have been managed better in these developing countries, and so we've seen a dramatic decrease in the death rate. The population, the birth rate shown here in red has remained stable until about 1955, and then it's dropped off, but it's still a large gap between birth rate and death rate. So developing countries are growing rather rapidly. Okay, so let's talk about the different stages. There are 5 stages that we will talk about here. Stage 1. In stage 1, you begin to see a decline in the death rate. Now, I'm going to show you the graphs for stage 1, stage 2, and stage 3. They're inferred here on these 2 graphs, but ignore these 2 graphs for now. Stage 1, like I said, there's a decline in death rates. Developed countries, this occurs in developed countries and developing countries. In stage 2 of this demographic transition is a period of high growth rate. In other words, the gap between birth rate and death rate begins to increase rapidly. And again, I'll show you that here in just a moment. Part of this has to do with industrialization. Death rate declines, birth rate stays high. In stage 3, now we begin to see the birth rate dropping toward the death rate. So the gap between birth and death begins to decrease, and so therefore the growth, the difference between birth and death, decreases as well. And part of this can occur as families were transitioning from larger families to smaller families. Think about it back, if you think about the early part of the 20th century, the 1900s through the 1930s, it wasn't unusual to see large families of 5, 6, 7, 8 children, and even larger. But as we begin to go forward in time, families started cutting back on the number of children, and so the birth rates would drop toward the death rate. So that is indicative of a stage 3 in terms of demographic transition. So for undeveloped countries, you take a look at the continent of Africa as an example. There has been improvement in education and living standards, health, family planning methods, and so now those rates have begun to decrease as well, the birth rates. And we see this back here, birth rates beginning to decrease in developing countries. Stage 4, there is actually a second decline in death rates. So that, once we begin to see that second decline in death rates, which if I go back here, you would see this here. That would be an example of stage 4. By the time you hit stage 5, that's represented by a second stable state that occurs when birth rates again decrease. So then birth rates begin to match death rates, and you reach a second stability in stage 5. So the key point here is that, according to your textbook, that if we decrease population, in other words, if parents believing having a smaller family is the way to go, then we would begin to stabilize population growth. Now let's talk about the different stages here. So you've got the crude rate here, both of birth and death rate, birth here in red, death in green, and then you have population going from low to high. So if we look at stage 1, so this is the original demographic transition, stages 1 through 3. We look here when birth rates and death rates are equal, which they are right here in from early stage 1 to about the middle part of stage 1. We see that population growth, there's very little population growth. It begins to become very stable. However, toward the end of stage 1, you notice here birth rates, while they are decreasing, the death rates are decreasing at an even higher rate. So now we're beginning to widen the gap between births and deaths. So at that point, with this ever-widening gap, you now enter into stage 2. And thus we see growing population in stage 2 as the gap between birth and death begins to increase. Now what ends up happening, birth rates begin to decrease, death rates are decreasing as well, and in fact they meet again down here. Now you're into stage 3, which means when death rates and birth rates are the same, the population begins to stabilize, although at a higher level than before. Because back in stage 2, birth rates exceeded death rates, we had a growing population, again they come together, and now we begin to stabilize. Now you notice here as you go from stage 3 into stage 4, birth rates early on in stage 4, we're now in a second transition, we've moved beyond stage 3, birth rates stay the same, however there's a secondary drop in death rates, and so we begin to see growing of population again. And finally, as we head into stage 5 here, the birth rates and the death rates are the same, population now stabilizes again, begin at a higher rate, and then after this second transition, now we begin to see, right here, death rates stay the same. However, birth rates begin to dip below death rates. Now, this is the first time we see this. This occurs after stage 5. And I'm not sure why they don't call it stage 6, but we'll leave it as is. But birth rates now are exceeded by death rates. And the death rate hasn't changed because notice it's a flat line here. It's just that births have decreased. And now we begin to see a decrease in population and a stable population, and it's even lower than it was back up here. So recall when we talked about the rapid fertility reduction rate, in other words, we went from 2.5 to 1.6 children per female, then we begin to see this decrease in population. This would be an example of that occurring. There are less births. Okay, we begin to decrease the amount of births, so therefore our population would begin to decrease. So really, you're probably getting the idea right now, the way to stabilize births, or the way to stabilize population growth, is to have less children or actually delay the time that children are born to a woman. In other words, in some of our developing countries, you read from the textbook, young women are getting married between 15 and 19 and having children at that time, whereas in developed countries, you're seeing now the average age of females giving birth is now 25. And so that would lead to typically lower number of children because the fertility, or actually the birth rate, has actually been increased from 15 years of age to 25. So what you see here, changes in birth and death rates in developed and developing countries. You see here from 1775 to 2000. We talk about the growth rate, which is the difference between birth and deaths. So we see here the growth rate was even in stage 1 in undeveloped countries. And then you begin to notice the birth rate exceeding the death rate, which leads us into stage 2. Stage 3, things begin to stabilize between the birth and death rate. And then the decline here, I should point out, the decline in deaths back here in stage 1 and stage 2, according to your textbook, has to do with basically improved resources such as sanitation and medical care, better medical care, controlling infectious diseases. And then note here now where death rates, here in green, begin to exceed birth rates. This is due to a decline in chronic diseases, and then you end up stabilizing here in stage 5. So there's a lot of information going on here. You may have to go back and review this part of the lecture a few more times, but it's fascinating to see how this all works together. So let's talk about longevity and its effect on population growth. So the maximum, we'll define, we have a couple of definitions here. The maximum lifetime is basically the maximum possible age to which a person or an individual in a species can live. And then the life expectancy is the average number of years an individual can expect to live. Here's some examples of life expectancies. In Japan, you see 82.1 years. So as of the writing of this textbook back in 2012, someone born in Japan could expect to live 82 years of age. Any idea why that might be? I mean, they have access to the same type of medicines and health care that all developed nations have. It probably has something to do with their diet. I suspect it's a much healthier diet. Swaziland, which I have no idea where that's at. Let me look it up here just a moment. You see, at 32 years, they have an average or a life expectancy of 32 years. I'm going to just look this up here a second. It's on the continent of Africa. Just going to pull it over here for you. And you see here Swaziland down here in the South Africa portion has the lowest life expectancy. There. So we talk about population growth has occurred throughout history with little change in maximum lifetime. We have had changes in birth rates and death rates, age structures you've seen from the graphs above, but in terms of maximum lifetime, that part hasn't changed in terms of population growth in the maximum lifetime. So it's obvious that life expectancy has increased throughout the last several hundred years, but population growth based upon that has not changed. Some of the reasons why we've reduced death rates, we've talked about just briefly: modern medicine, better sanitation, access to better foods, an increase in agricultural trying to think of the word I'm looking for. Yields have increased. We talk about acute diseases and chronic diseases. Chronic diseases, When you think of acute diseases, you think of things like SARS, about Legionnaire's disease, the Black Plague. Those are things that appeared rapidly in population and then basically disappeared. It says here that about 60% of deaths occur in Ecuador because of acute diseases, whereas only 20% of the population in the U.S. has a mortality rate of 1 in 5. And that has to do with the access to better medicine, more readily accessible. However, if you look at chronic diseases, so for instance, like heart disease, diabetes, the U.S. has a mortality rate of 70% compared to 20% in Ecuador. And that certainly has something to do with our diet that we have. And then you can see here in one of the tables, it talks about the different causes of mortality. So you look at the U.S. back in 1900 when we were beginning to industrialize. Actually, we were 150 years into industrialization. But you see that about 16% of the mortality was related to respiratory diseases. Now you look in 1998, respiratory diseases make up a very small percentage here. Well, let's see, where's the respiratory? In fact, I can't even find it. Let's look at something else here. Let's look at infectious and parasitic diseases. About 8% of the U.S., the mortality rate was 8% from infectious and parasitic diseases in 1900. And now I can't even find it over here. So you can see as we've gone 100 years into the future how that has changed. Okay, let's spend a little time talking about the effects that human population has on the earth. We know that all humans pose some sort of threat to the environment. And in fact, we can actually quantify this with an equation. You see what you have right there. You've got the equation T is equal to P times I, where T is the measurement of the total impact of the human population on the environment. P is the average impact of an individual. So like you and I would have an individual impact on our environment. So for instance, driving cars that burn fossil fuels kicks out a lot of CO2. We leave a carbon footprint. We'll talk about that later in this course when we get to the global climate change aspect of it. But we each leave an imprint on our environment. And if we multiply that, this actually should be I and not T. That's a mistake on my part there. I is the total number of individuals. So T is the total impact. We can measure the total impact that we have on the environment by taking a look at the average impact of you and I and multiplying that by the number of individuals or humans on the earth. So, for example, just kind of looking down here, an example, if you look at the population of Bangladesh, your textbook uses this as an example. It has a very large population, which is the total number of individuals here. But the average impact of an individual in Bangladesh on the environment is smaller compared to the U.S. Okay? If you look at the amount of fossil fuel burning cars in Bangladesh compared to the U.S., would be less. So the footprint is less. However, the number of individuals is quite a bit more. So even though they might have fewer cars or fewer fossil fuel burning type of machinery, they have a lot larger population. So they would make a rather large impact as well. So either one of these, the average impact or the number of individuals, play a role in the total impact or the total footprint that we leave on the environment. So we know that basically as a society begins to modernize, begins to industrialize, we begin to use more resources, And by doing that will greatly enhance the impact we have on the environment. Your textbook talks about chlorofluorocarbons. Chlorofluorocarbons were used as a propellant of underarm deodorant back in the 70s. CFCs were used in the 70s and 80s as refrigerants in your air conditioners. And so we were putting out all of these CFCs into the atmosphere, which was breaking up ozone, which is 3 atoms of oxygen, breaking them off into diatomic oxygen, O2, and a single atom of oxygen. And so then we were letting in more ultraviolet radiation, which was creating issues for like skin cancer, skin disease back in the 70s, 80s, and 90s. Automobiles releasing CO2. So while technology is great, it also acts to diminish or deplete resources, the natural resources we have here on the earth. And the byproducts of those of technology can actually serve to destroy or certainly hurt our environment. I did it again. Sorry, I have to go back here. Hope I'm not getting you dizzy here. So the question comes, how many people can we get on Earth at the same time? Now notice how I phrase that question. How many can we put on the Earth? We can put quite a bit more than what we have right now. However, can we continue to live with the same comfort that we have with an increasing population? So think about it now. Your children, they will have children. And so as we continue to advance medicine, the birth rates might stay the same, but the death rates begin to decrease. And as we saw before, the population will continue to increase. So we would hope that our children would have the same standard of living that we have now. Chances are, though, that's not going to be true. Your textbook talks about depleting aquifers. These are aquifers supply us water. So we have decreased water availability as we go into the future. So there will be some trade-offs as we continue to increase population. Yes, we can put more people on the earth, but can we maintain the same type of living that we're used to? It's probably not going to happen. Our children, more specifically our grandchildren, will probably live in an environment that there will be challenges, such as water availability, fuel availability, those types of things. Increased population will lead to more infectious diseases. So those types of things we have to look at. So basically we're talking about the quality of life. There are 3 types of ways that we can estimate the human carrying capacity. We can use extrapolation from past growth. We've already talked about that. We've talked about exponential growth, logistical growth. We've got this thing called the packing problem approach, which we just continue to stack people on Earth. And like I said, we can still fit more people on Earth. However, more people on Earth is going to create more challenges on our resources. And then this thing called deep ecology, really fascinating. The idea behind deep ecology is that we are making a negative footprint on Earth. And so the one way to take care of this issue is to decrease the size of the population. In other words, some ideas may be that we limit families to 1 child per family. Over in Asia, there has been for a long time been an upper limit of children that a family can have. And so the idea behind deep ecology is to make a substantial decrease in the size of population based upon, in one way, decreasing the number of births. There's probably somewhere in between this packing problem approach and deep ecology, there's a solution in that area. Let's talk about some limiting factors to the human carrying capacity of the Earth. Food shortages. So there are three terms that we use: short-term, intermediate terms, long terms. Short-term are impacts that we see in less than a year. So you see food shortages over in the continent of Africa, different parts of the world. That is a limiting factor of our carrying capacity. Things that affect our population in a decade or less. You see desertification. In other words, this is when areas that were basically lakes, aquifers, now begin to dry out completely, and all you have left is deserts. The pollutants that we put out in the air, they may not impact us in a year or maybe 2 years, but after a decade, we'll begin to see the negative impacts that pollutants. CFC was the perfect example. It took several years before we begin to see a noticeable decrease in the ozone layer due to CFCs being put up into the atmosphere. And then long-term effects, anything from a decade and beyond. One thing that comes to mind immediately is climate change. You see various models that predict out 50 to 100 years that show changes in temperature, increased change in temperatures. That is a long-term effect. There's a couple of other examples there: soil erosion and groundwater supply decrease in aquifers. So the question comes now: if we were to go to this deep ecology approach, can we achieve zero population growth? If we look back in history, if we look at the birth rates and death rates, if we go back from 1775 to the early 1990s, we certainly have not achieved zero population growth. Now, theoretically, we can, if birth rates and death rates are the same. So see, there's zero population growth right there in stage 3. And in fact, if you look back here, 1775 to 2000, like I said, in a stage 3, that would give you a stable population growth. But that is the $64,000 question. Can we achieve it? You see some of the approaches there. I talked about earlier in this lecture about delaying the age of first childbearing. Obviously, the older the individual is having their first child will also delay or actually decrease the percentages of having more children. Birth control, it's been around in the pharmaceutical world since the early 1960s, and then you have programs that are out there to reduce birth rates, education, increase access to birth control. So there are ways out there, but personally I don't think we will ever achieve zero population growth. I think there are just too many factors to account for, but again, that's my opinion on this. That might be a good discussion question for everyone. I'll have to think about that. Okay, let's just summarize this chapter. There's a lot of information there, a lot of interesting information, but you see there that human population, the reason we covered this in this course is because it is a major player on environmental issues. We have such a huge impact on our environment and on other species that we certainly need to understand some of the basic characteristics of population dynamics. We talked about how the human population can be divided into major phases. We've seen that population has increased in each phase. The current situation, like we said, is unprecedented. We haven't seen it like this in history before. We talked about demographic transition, stages 1 through 5 there. We see that developing nations, such as Africa, have undergone a great decline in their death rates, but they still have very high birth rates. Birth rates exceed the death rates, so their population is still growing. So one question here that we can look at is, can these developing nations achieve a lower birth rate before reaching a disastrously high population level? Some controversial questions that we've introduced: the maximum population, and what size will we ultimately attain? Here's some estimates for future. 10 to 16 billion before stabilizing is what has been estimated. We've also talked about how we may stabilize population. However, when we do that, we're not just talking science, we're also talking values, we're talking religion, we're talking what we are used to living with, a standard of living. And we've identified here in the end, one of the ways to stabilize a population is to lower the age of first childbearing. That is not true. Ha! It says here, one of the most effective ways to lower population's growth rate is actually to increase the age of first childbearing. Sorry, that is a mistake there. So again, the way we do that is not lower. We want to raise it. So if we raise it from 15 to 25, for instance, then odds are pretty good, percentages are pretty good, that the number of children in that family will be less than if the family started at a younger age. So, I hope you've enjoyed this brief discussion on population, and have a good day.